Hi, my name is Brandon Banks, and today I'll be discussing multi-loop circuits. Now, as we know, multi-loop circuits are different from circuits because they have two EMFs. And when current flows through it, there's a break-off point that splits into two separate currents, and then it comes back at a different point into that same one current. Now, this is just a basic example of a multi-loop circuit, and you can see everything that I explained before. Now, with those three equations that I wrote over there, they're color. So, like I said earlier, when current breaks off, it broke off at point A and it split into current 1, current 2, came back, point B, came together. That's how I got equation 1, I3 is equal to I1 plus I2. Now, equation number 2 is a bit more complicated. So when you're calculating the current for a multi-loop circuit, you have multiple possibilities. You can break this little section into a cycle, this little section into a cycle, or you can do the whole part. In this case, I decided to do this section as a cycle and the whole one. So I started at point B. Now going across the EMF, I end at the high potential side, which means there's more of a charge there, which is the reason why I have positive 5. Now, as I go across the resistors, I'm going with the current. Now, if I go with the current, that means the value added to this equation is negative. And if I go against the current, the resistors, the value of the resistors is positive, and you'll see that in a minute. So part B, and I'm going through the EMF, positive 5, so plus 5, minus 10, go to point A, go up, I'm still flowing with the current, and as you can see, this is my overall equation at the end. Now, with part 3, I do the whole thing. I'm still starting at point B. Now, point B, and I go down, and now current 2 is coming around, so I'm going against it, so plus 7 ohms, and now I hit the EMF, and I'm going to the low potential side, which is the reason why I have minus 10 here. Go up past A, I, and finish it off. So these were my overall equations. Now, as you can see in equation 3, in equation 2, I have I3 and I1, I2 and I1. But I'm looking I3. So there's a way I can manipulate these equations where I can get I1 so I can solve for the rest of them, which is I1 is equal to I3 minus I2. Now, I can solve this for I3, and I can solve this for I2. So 10 I3 is equal to 3 I1 minus 5. That's wrong. My bad. Is equal to 0.5 minus 0.3 I1. And now when I solve for I2, I2 is equal to 10 plus 3 I1. And when I divide it by 7, I get I2 is equal to 1.43 minus, no, plus. I'm going to get this right one of these days, for 43 I1. So now that I have I3 and I2, I can solve for I1. So 0.5 minus 0.3 I1 minus 1.43 plus 0.43 I1. Now when I add my like terms, I get negative 0.93 minus 0.73 I1, which is still I1 right here. Now I'm going to solve for I1, which means it's 1.73 equal to I1 is equal to negative 0.93 which means I1 is equal to negative 0.54. Now that I have that, all I have to do is plug I1 into either I2 equation or I3 equation. Or I3 equation. The equation I'm actually going to use is I3. So I'm going to plug I3 is equal to 0.5 minus 0.3 I1, where I1 is negative 0.54. So I3 ends up being 0.33. Crap, that's wrong. No, it's not. 0.338. Now, all I have to do is manipulate equation 1 again to find I2. So I3 is equal to I1 plus I2. I2 is equal to I3 minus I1, which means 0.338 minus negative 0.54 means I2 is equal to 0.878. And those are my three currents. And I just realized that when you add, so now that we have all three, we can check. So I3 is equal to I1 plus I2. So I3 is equal to negative 0.54 minus 8.78. I3 is equal to 0.338. And that is multi-loop circuits.